Folks, looking at this chart, we've seen this chart before. This is our conversion chart that we used back when we learned that you can go from mass to mole and mole to mass. If you know mass, you always know moles. If you know moles, you always know mass. All you need is what? All you need is a periodic table. You look up the molar mass. Do you remember this conversion chart? If you know moles, you know volume. Assuming it is a gas. If you know volume, you know moles. All you need is the molar volume of gas, 22.4. We also know that if you know moles, you know the quantity count. The quantity count, you know moles. All you need is Avogadro's number. Moles are the unifying concept in chemistry. Everything is related to moles. We mentioned earlier we would come back to this chart. Earlier this year, we mentioned we would come back to this chart after we've got through Unit 8. And we are now back. Because when you look at this chart, you should feel oddly off balance. Because we can go west to mass from moles. We can go north to volume from moles. We can go south to quantity count from moles. We can go this way, this way, this way. But we have no that way. Doesn't that make you feel out of balance a little bit? If moles is the center of everything, we've got this, we've got this, we've got this, nothing over there. There's an uncharted area over here. An undiscovered land lies to the east. Look at this. It's fabulously fascinating. What is out there? What is out here in the untraveled, undiscovered world? Like if you're traveling from moles, are you just going to fall off the face of the chart? Sort of like was believed back in the days of our great explorers, who at one time thought the world was what? Flat. They felt if you sailed, you would reach the end of the earth and fall off. Is that what's happening here? We can go this way, we can go this way, we can go this way. What is that way? What is out here? In this undiscovered world of chemistry, what is out here? The answer, we've already discovered it. You may not know you've discovered it. But there is something out there to be discovered. Because we now can relate moles to something else. And we learned it in Unit 8. There is something else out here in this uncharted territory. What is it you say lies out this way? It's moles. We can convert moles of one thing to moles of another thing. It is moles that lies out here in this uncharted, undiscovered world. It's moles. We now can successfully relate moles of one thing to moles of another thing. We have an arrow that will now take us this direction. What is it that relates moles of one thing to moles of another thing? That is the question. Let me show you this. Synthesis, reaction. And you will now know what I'm talking about. I have to add some heat energy to this. If I take hydrogen gas, maybe in a balloon, and I insert a burning splint into the balloon, it's going to burn. And we would make water. What am I saying relates moles of one thing to moles of another? I will just ask you this simple question. How many moles of oxygen would I need to burn 2 moles of hydrogen? How many moles of oxygen would I need to burn 2 moles of hydrogen? Jason has it here in the back. He says, it is 1. Sir, where did you get the number 1?
Because it's turning into H2O, there's 2 H's or 2 H2s.
I have 2 H2s, and for every 2 H2s, I need how many O2s? 1. The coefficients. If I am burning 2 moles of hydrogen, I need 1 mole of oxygen. How many moles of water would I make? And this would be gas, not liquid. How many moles of water would I make? 2. We can relate moles of one thing to moles of another thing if we have a balanced chemical equation, which now should clarify why we spent so many days, if not weeks, understanding and learning to write and balance chemical equations. Let's say it was a day much hotter than today, and you needed water. You are thirsty. Maybe you have activities after school and you need to hydrate. You're like, hydrate. And you're like, how much water should I drink? Let's say you need to drink 4 moles of water. 4 moles of water. Question, if you need to make 4 moles of water, how many moles of hydrogen gas would you have to burn? Assuming we have plenty of oxygen and we do, it's in the atmosphere. How many moles of hydrogen would you have to burn to get 4 moles of water? Take a shot at it. You said 8. Does anybody agree with 8? How did he get this? Very well done. We are going to use the way we learned to set these up. The question is, how many moles of hydrogen would we need to burn in order to, our given is right here. Do you remember doing these kind of problems? We write the question first, then we write our given. We want 4 moles of water. Yes? And then we have to establish a conversion factor. We have to establish conversion factors. Let's do this a little more clearly. The question is, how many moles of hydrogen would we need to burn in order to get 4 moles of water? Here's our given. Here's my question. Question mark. Moles of hydrogen. My given goes right here at the front of the problem. 4 moles of water. Now I need some conversion factors, and the conversion factors come right from our equation. I need to know moles of hydrogen to moles of water. From this equation, I know that it's 2 moles of hydrogen for every what? 2 moles of water. Yes? Is that correct? Now, we also can write it this way. There are 2 moles of water. That's on top. for every 2 moles of hydrogen on the bottom. Now we've got to plug these in to see if our guess was right. Our guess was how many? 8. Is our guess right now that you're looking? Two moles of hydrogen for every 2 moles of water. Which of these conversions am I going to pick? The left one or the right one? Well, I'm given moles of hydrogen, so the conversion I need will be the one with what on the bottom? We're given moles of water. The conversion I'm going to need is the one with where? Moles of water on the bottom, yes? So we're going to pick the conversion. 2 moles of water on the bottom. What's the conversion on top? Wherever I'm converting to needs to be on top. It's 2 moles of hydrogen on top. Is our prediction going to be correct? Oops, it's H. Yeah, let's put that correct. Thank you. Good eye, good eye, good eye. H2 over H2O. We're picking this conversion right here. Now, moles of hydrogen cancel out with moles of hydrogen. We're looking to convert it to moles, or moles of water can cancel out with moles of water. We're trying to convert it to moles of hydrogen. So moles of hydrogen will be what is left here. This unit cancels with this unit. We're left with the unit we want. So we have 4 times 2, yes? What? 4 times 2 divided by 2 is what? 4 times 2 is 8. Divided by 2 is 4. What was the question? Yes. So we were thinking it was going to be 8 when we set the problem up. And this is why we set the problem up. We can see 4 times 2 is 8, but we forgot that it was 2 to 2, which is essentially 1 to 1. The question comes down to when we set up these conversions, I do not reduce it to 1 to 1. These numbers must be what we see in our balanced chemical equation. So whatever numbers we see here need to be in our setups. Now, when you actually do the mathematics, if you want to reduce those, you can. But make sure that you leave the 2 and the 2 there. These come straight from the equation. Yes? This is how we use the equations. This is how we use the balanced chemical equations. It opens up this entirely new. It opens up this entirely new. Oh, this thing is going to have to get some repair here. It usually does not happen this way this early. Can we get it? Can we get it? No, we're going to have to start it up. But it's at a convenient time to start it up. And here's why. We now have realized that we have a whole new place that we can go on our conversions. We have a whole new place, a whole new territory to go to. But the real question is, how big is this territory? Just how big is the territory we are talking about converting to? And I am going to come out and say this, it might be bigger than you even ponder at this time. This new uncharted place that we can convert to, once we've learned to master this mole-to-mole conversion, will open up an uncharted area that we never knew existed. A balanced chemical equation gives us great power. It gives us great power. And let's take a look at what great power we have now unleashed. The last chart we just looked at. The last chart we just looked at. The chart we were very familiar with. We knew we could go moles to mass. We knew we could go moles to volume. And we can also go moles to quantity count. But today we learned if we have a balanced chemical equation, we can go from moles of one thing to moles of another. With the balanced chemical equation, we convert moles to moles. This is the one we're learning to do today. But once we've done this conversion, it opens up a whole new part of the chart. If you know the volume of a gas at STP, the mass of a substance, the quantity count of the substance, or the moles of a substance, and you have a balanced chemical equation, we can convert it to moles of something else. It should not be beyond your ability to understand that if you convert it to moles of something else, you could also find the volume of what that substance is. If it is a gas at STP, we should be able to find the mass of that substance, and we should be able to find the quantity count of that substance. So if you know the volume, the mass, the moles, or the quantity count of one thing, and you have a balanced chemical equation, you can find the volume if it's a gas, the moles, you can find the quantity count, or the, whichever one I forgot to say, the mass, or the moles of another thing. The power of this chart, the power of the moles concept, the power of a balanced chemical equation is now unleashed. You are now able to do chemistry. Because we were just talking about moles. In our very last example, we were saying we needed 4 moles of water. And with the balanced chemical equation, yes? With the balanced chemical equation, if we wanted 4 moles of water, we found out we needed 4 moles of hydrogen gas. But there are no balances that measure in moles. Balances measure in what? Mass. So how are we going to know how many, if we want 4 moles of water, that is really a mass of water. Or if it's a gas, it would be a volume up here. And when we want to know how much hydrogen we would want or need to make that water, we're not going to want to put the hydrogen on a balance. That's difficult. Hydrogen's lighter than air. How do you mass it? But we could use the volume of hydrogen gas we would need. So if I know the volume of water at a gas state, or for instance, if I know the mass of water that I want, I can find out how much of any of these other substances we would need to make it. It would just involve converting along this chart, this beautiful chart, and that is what we're going to learn to do in Unit 9. Today, we're going to learn to do the initial conversion. Moles of one thing to moles of another thing using a balanced chemical equation. Tomorrow, we're going to learn to go to mass of one thing to mass of another thing. Tomorrow, you're going to do one of the most fundamentally significant calculations in all of chemistry. If you know the mass of one thing in a chemical reaction, finding the mass of another thing in that chemical reaction. That is tomorrow's calculation. But to do mass to mass, we first need to learn to do mole to mole. Be sure you have your Chromebooks tomorrow. They've been talking today about coming with as little as you can to school tomorrow on the seniors' last day. But you will need your Chromebooks for this class. Let's move on now to learning our first mole-to-mole calculation Waiting for you on Google Classroom are some introductory videos and practice problems. We begin our final unit, Unit 9. Good luck, students.